So in this lesson, we are going to be covering the method of proof by contradiction and the method of proof by induction. Proof by contradiction, that's going to be section 3.2 of our textbook, whereas induction is going to be 6.1 of our text. I am going to do things slightly different in terms of the examples that I'll cover in the lecture than what the book does. So specifically, we will be proving that there are infinitely many primes and that the square root of 2 is irrational. We will also return back to one of our motivational examples in our first lesson, that the sum of the first n odd positive integers is equal to n squared. And so we're going to prove that using induction. So let us begin with proof by contradiction. So this is also referred to in Latin as a reductio ad absurdum argument. So in other words, a reduction to absurdity. Now, the way that it works is as follows. So throughout, I'm going to go ahead and suppose that P, Q, and C are propositions. And so let us suppose that we wanted to show that P is true. So we want to show, which I'm going to abbreviate to WTS, P is true. In a proof by contradiction, we want to assume the negation of P. So assume not P. So then, we want to show that not P implies some contradiction C and not C. Now, the way that this is constructed, we're saying that now this implication is true. But if we think about it in terms of the truth table, or even better, if we use the conditional law, we know that this here is logically equivalent to not P, so in other words, P, or C and not C. But C and not C, this is a contradiction. Oops, and I forgot parentheses. But this is a contradiction. So by the contradiction law, this is logically equivalent to P. So in other words, this statement here is true if P is true. So thus, not P implies C and not C is true if and only if P is true. And that's the basis for a proof by contradiction, is that we want to deduce some contradiction. And that, in essence, will have to imply that what we wanted to show is actually true. And so that's one method for proof by contradiction. On a related note, suppose that we wanted to show instead that P implies Q. In this situation, we do the same thing. We assume, so in this case we are assuming P, and we want to show Q. So now we assume not P. We assume not Q, and show of the form. So we're going to give an argument of the form P and not Q implies some contradiction. Then we do the same thing we did above. We go about finding the logical equivalent statement to this. And so we will have not of this or the contradiction. But by De Morgan's law, this becomes not P or Q or C and not C. But now the contradiction law tells us that this is just not P or Q contradiction law here. But now this is the same in this situation as Q. The reason for this is that we are assuming P, and so we are assuming that P is a true statement, and so not P is false, and so if this is true, we have that Q must be true. So what we end up getting is that the implication is true if and only if Q is true. And so that's what we wanted to show. We wanted to show that Q was true, and so now we have a way of deducing it. And so this is the logical construct when we break everything down into its proposition and logical connectives. What we are going to do now is do explicit examples and then return back to this slide and compare what we just did and see how that argument matches up. Because what is not clear here is, what is that contradiction? What is it going to be? So for our first example of a proof by contradiction, we are going to revisit the famed proof of the irrationality of 2. So this dates back to the Pythagoreans in 450 BCE. Legend has it that Hippasus of Metapontum, a Pythagorean, was the first to discover this proof. But in doing so, he also showed the existence of irrational numbers, which went against the mathematics of the Pythagoreans, who believed that everything in math could be built from the positive integers. In the case of the positive rational numbers, we can construct them from the integers. If we have 1/2, that's a ratio of 2 integers. And since this went against their core belief, they murdered Hippasus at sea. Now, this is a legend. There's a lot of things that can be questioned about it. For one, the Pythagoreans historically were a pacifist group, and so murdering someone for proving that the square root of 2 was irrational is a bit of a stretch, but this is a story that has survived the test of time, and so you'll most likely hear the story in other math courses. So with that, let us go ahead and see how to prove this via contradiction. So we want to prove that the square root of 2 is irrational, and so what we are going to do is assume the negation of this. So assume that the square root of 2 is rational. So let's do our scratch work. So we're going to assume that square root of 2 is rational. And this is a symbol we use at the start of the term when introducing notations. I'm just going to write this as a reminder. So another way of writing this is the square root of 2 is in Q, where Q is the symbol for the rational numbers. So this tells us that there exists some integers a and b such that the square root of 2 is equal to a over b. If we then square both sides, we get 2 is equal to a squared over b squared. And we can go ahead, multiply by b squared, and have 2b squared is equal to a squared. But then, we have that a squared is even. And if we come back to earlier in last week, we have proven the following statement. So we have proven that if x squared is an even integer, then x is an even integer. So this was our first example of seeing how the contrapositive could be used to prove a mathematical statement. But now if we use this lemma, we can get that a is even. But now if a is even, the definition tells us that a is equal to 2k for some integer k. But now, if we come back and plug in we get 2b squared is equal to 4k squared. We can go ahead, divide by 2, and we get that this here is going to be b squared is equal to 2k squared, which then implies that b is even. Sorry, b squared is even, and now the lemma implies that b is equal to 2l for some l in Z. But now, what is the problem as of now? There doesn't seem to be a contradiction yet, but here is where we can use the scratch work as a guide. We have proven that A is even and B is even. But when looking at square root of 2 and the way we chose it to be some integers A and B because it was some fraction. But when dealing with fractions, say 2 over 4, so that's a possibility where both A and B are even. But this is also the same as 6 over 12, which is the same as 1/2. So we use the following fact. Every rational number can be written in simplified form so in other words, A over B with the GCD of A and B being equal to 1. So that is, A and B have no common factors. Other than 1. So if we use that fact, then what we have now shown is that we can start off with A and B being relatively prime, but then they have a common factor of 2 because both A and B is even. And that's the contradiction that we are getting in this situation. But we need to now take that into account. So the reason I worked it this way in the scratch work is that I didn't take that assumption that the GCD was equal to 1, but then included it afterwards to get the contradiction. But this sometimes happens when we write proofs. We do the scratch work and then we realize, oh, we could put this extra assumption and that will give us the contradiction that we need. And that's why it's good to write the proof afterwards. So let's write this proof formally. So we're going to go through the same argument, but now write it in a precise manner. And so the first thing we want to do is inform the reader that we are going to be doing this via a proof by contradiction. And so one way of doing that, and I'll write several. So we can start off the proof by saying towards a contradiction. Assume that the square root of 2 is irrational. Is rational. Then there exists integers A and B, and now I'm putting in that GCD of A and B being equal to 1, such that the square root of 2 is equal to A over B. Now observe that square root of 2 is equal to A over B implies that 2 is equal to A squared, B squared. And so here we squared both sides. Then we multiply by the B squared, and we get 2B squared is equal to A squared. So therefore, a squared is even by the lemma, and oftentimes the lemmas may have a number, so in this case there is no ambiguity since we have only one lemma in this slide. But if I had labeled this, say, lemma 1, then we would say by lemma 1. And a common thing in mathematics is that we capitalize whenever we're referencing a numbered statement. So in this case, lemma 1, we capitalize the L. So by lemma 1, we have that A is even. So now A is equal to 2k for some integer k. Thus, 2b squared is equal to 4k squared, which is equivalent, upon dividing by 2, to b squared is equal to 2k squared. So in particular, b squared is even, and by lemma 1, so now I've capitalized lemma again, b is equal to 2l for some integer l. But then the GCD 2 is a factor of the GCD of a comma b, which contradicts our assumption that the GCD of a and b was equal to 1. Hence, the square root of 2 is irrational. And so we are done. So we have now completed the proof. But now, if we come back and trace the argument, we see that the contradiction, so if we come back to the way that we were talking about this initially, we start off with, we want to prove that the square root of 2 is irrational, so we assumed not p, where p is square root of 2 is irrational, so that's not p. And what we saw is that the contradiction statement C is that the GCD of a and b is equal to 1, and the GCD of a and b is not equal to 1. And so that was our contradiction. But it was not that we got to this implication from one step, but we gave a series of arguments that eventually leads to this contradiction. Because what we have is that we assume the square root of 2 is rational, and so then that implies our proposition C, the GCD of a and b is equal to 1, upon we write square root of 2 as a fraction of the form a over b. And then we continue going through this process, through this logical argument, having the implications along the way, until we get that 2 is a factor of the GCD of a and b, which is equivalent to saying that the GCD of a and b is not equal to 1. And so now we have, putting everything together, that the square root of 2 is rational implies C and not C, which is our contradiction. So in our last lesson, we talked about the notion of what it means for a number to have a factor. So specifically, we define for some integer a that a integer d is a factor of a if we can find some integer k such that a can be written as d times k. Now we can define formally what it means to be a prime number. We say a natural number p with p greater than 1 is prime if the only factors of p are 1 and p. If p is not prime, so in other words, if we have now some natural number n with n greater than 1, and it is not prime, then we say that n is composite. Note that this here is equivalent so this says that if n is composite, then there exists natural numbers a and b with 1 strictly less than a comma b, so both a and b are greater than 1, and both are less than n, such that n is equal to a times b. Building on these two definitions, we are going to prove the following lemma, which will be our building block towards proving that there are infinitely many primes. And so the lemma states that if n is an integer greater than 1, and a is the smallest factor of n that is greater than 1, then a is prime. So now, here's proof, and I'm going to skip the scratch work in this case and just go to the proof directly. And so let's go ahead and write down our assumptions. So we're assuming, so suppose n is an integer greater than 1, is an integer with a greater than 1, the smallest factor of n. And so those are our givens. And we're going to do this by contradiction. So we're going to suppose that a is not prime. So in other words, a is composite. So now what we are going to do is inform the reader that we are going to do a proof by contradiction. So let's go ahead and inform the reader. So assume, for sake of contradiction, that a is composite. Then there exists, so there are integers, let's go ahead and call them k and l, such that a is equal to kl and 1 is less than k, l, which are all less than a. Now we're going to come back to the fact that a is a factor of n. Since a is a factor of n, there is a integer d. So there's an integer d such that a is equal to, n is equal to d times a. So in particular, n is equal to d times a, but we have already established that a is equal to k times l. And so now we have n is equal to d times k times l. So k is a factor of n with 1 less than k, which is less than a. But this is a contradiction, because now we have that k is a smaller factor of n than a. But this contradicts our assumption that a is the smallest factor of n that is greater than 1. Thus, so therefore, a is prime. And we are done. We have our proof. So now, let us analyze this proof. So this was a proof of the form P implies Q, where Q is A is prime. And so what we did was assume P and not Q. And what we ended up deducing is that P and not Q implies our proposition C, which is the smallest factor of n that is greater than 1 is A, and A is not the smallest factor of n that is greater than 1. And so that's our C. And so this was an instance of a proof by contradiction where we have P implies Q. And so now we showed that there is some proposition C in our argument such that P and not Q implies C and not C. And so we can conclude that Q is the case. And so in this case, Q being A is prime. So next we are going to prove the following useful result known as the linear combination lemma. And so this result tells us that if we have integers n and m, if d is a factor of both n and m, then d is a factor of n plus m. And so here's the proof. We can do this directly. So let's go ahead and, so here we have let n and be integers with d a factor of both n and m. So by definition, there are integers k and l such that n is equal to d times k and m is equal to d times l. Therefore, n plus m is equal to d times k plus d times l, and we can factor out a d, and so this is equal to d times parentheses k plus l. And so this shows that d is a factor of n plus m. And so we're done. Now, armed with the linear combination lemma and lemma 2, we can now prove the famed infinitude of the primes. And so this is due to Euclid around 300 BCE. And the way that the proof goes, and I'm going to do it by contradiction, but I'm going to omit the scratch work in this case and just write down the proof formally. And so here's the argument. So assume, for sake of a contradiction, that there are finitely many primes. But if there are finitely many primes, then we can list them. So in particular, we may assume that all the primes appear in the following list. So we have 2, which I'm going to label as p sub 1, the first prime. Then we can take 3, which I'm going to label as p sub 2. We have 5, which is the third prime, p sub 3. And we can continue in this manner until we get to some p sub n, where p sub n is the greatest prime. And so we have our list of prime numbers. And now what we are going to do is take the product of each of these primes. And so we're going to go ahead and let n be equal to the product of p1 times p2 times p3. And we just continue multiplying until we get to p sub n. Oops, and I want to write this as capital N, since we already have the subscript n as the lowercase n as a subscript here, so let's write that as capital N. And so we have this product of numbers, and as a side note, later in the course we're going to also introduce this symbol, the capital Greek letter pi. And so we can write in the same way as we write with infinite sums or finite sums with a sigma notation. We can also write here this notation where we have the product of the p sub j's is equal to capital N. And so this is a shorthand way of writing this product. And so that's just a side note, but we'll introduce this notation later on. And so we have capital N is equal to P1 all the way through Pn. Then P sub n is strictly less than n plus 1, because P sub n, the largest prime, is a factor of capital N, and therefore P sub n has to be strictly less than capital N. And so it also is strictly less than n plus 1. And so P sub n is less than n plus 1, and thus n plus 1 is not prime, since P sub n is the greatest prime. Now we use lemma 2. So by lemma 2, we have that if we have a composite number and we look at the smallest factor, but we know it's composite, so it has factors. So the moment we look at the smallest factor that is greater than 1, we have that that factor must be prime. And so in particular, so by lemma 2, n plus 1 has a prime factor. Say q. So here we're labeling q as the prime factor of n plus 1. By construction, q is a factor of n, because n is the product of all the primes, and so q is prime, so it has to appear in this list of primes that we're multiplying. So q is a factor of n, and now we use the linear combination lemma. So by lemma 3, we have that n plus 1, we have that q is a factor of n plus 1 minus n, which is equal to 1. But we have that this is a contradiction, because now we have that q is a prime, and that tells us that q is at least 2, but the only factor of 1 is 1 and negative 1. And so this here, so q is a factor of 1. And so I'm going to write this down here, so which implies that q is equal to 1, which is a contradiction. Therefore, there are infinitely many primes. And we are done. We have finished the proof. And so now we have established that there are infinitely many prime numbers. So next up are the rules of inference in logic. When we do proofs, sometimes these are used implicitly, and we can derive these from truth tables. So if P and P implies Q are true, then Q is true. Now this here is just an adherence to the truth table. So if we have true and true for this, the only way that P implies Q is true, with P being true, is if Q is true. And so that's just a restatement of that fact. And so this is called modus ponens. And similarly, if Q is false and P implies Q is true, so now we have false here, then the only way that this is true is if P is false. And so that's modus tollens. And what we are going to do now is use these rules of inference to deduce the following statement. So the following statement is in terms of a if, where we have a conditional for our assumption, and then our conclusion is also a conditional. But then both the assumption and conclusion, while they're conditionals, their assumptions also have a conclusion that is a conditional. So how does one prove a statement of this form? Well, in such a proof, we want to assume, as always, we assume the assumption. So assume P implies Q implies R. But we're also going to be assuming P and not R. And so we have P and not R. So we assume P, since that is the assumption here for Q implies R, so we're going to assume that P is true. But in order to prove this, we are also going to assume that not R is true. And then we want to prove that P implies not Q. So it suffices to show that P implies not Q. But now we can use the rules of inference, because now we have P, and P implies parentheses Q implies R, and so modus ponens tells us that if we have P and P implies Q are true, which is what we're assuming, where now the Q's of course are different. The Q here is Q implies R. So now we get that Q implies R is the case. So we can say by modus ponens so we have that Q implies R. But now we come to modus tollens, because here we have Q implies R, but we also have not R. And so now if not R is true, then R is false. And if we have that R is false and Q implies R is true, which is what we have here, and this is in the argument that Q implies R is true, we must have then that Q is false. And so that's what we're using here. And so, by modus tollens, it is the case that not Q holds. But keep in mind that here, since we're doing a mathematical proof, we're taking, when I say not Q holds, that means that not Q is true. And so we're assuming P, so P is true, not Q is true, so P implies not Q is true. And so hence we have P implies not Q, and consequently not R implies P, which implies not Q, since not R was part of our assumption, and now we have gone through with this assumption to get that assuming this, we do get back P implies not Q. And so we are done with the proof. And I'll mention that in our text, there is a couple of more pages devoted to this than what I have done, and so please look through page 109, page 109 and 110 for further elaboration on this example. So next we are going to move on towards the principle of mathematical induction. And what it says is, if P of n is a statement for each natural number n, and it is established that both P of 0 is true, which we call the base case, and for each natural number k, if P of k is true, then P of k plus 1 is also true. Then P of n is true for each natural number n. Now, we are not going to prove the principle of mathematical induction, but I'll just mention briefly that from the axioms upon which arithmetic is based off of in set theory, so these are the Zermelo-Franco axioms that I mentioned previously, one can prove the principle of mathematical induction. For our course, we are going to take the principle of mathematical induction as an axiom and just assume it to be true. But in a further course in logic, one can actually prove this statement from the given axioms here. So now let us recall the example that we did in our first lecture. So we saw that if we add the first n odd numbers, that we get back n squared. And so we had a conjecture. The sum of the first n odd positive integers is equal to n squared. We can now use the principle of mathematical induction to prove this result. So now let us go ahead and show that the sum of the first n odd integers is equal to n squared. Now what I'm going to do is a quick modification to the principle of mathematical induction. The way that it's phrased here, we have to start at 0. So we're doing it for every natural number. But actually if we start at 1, that's also perfectly fine. So for example, if I put here n plus, where the natural numbers plus, I mean the positive integers, since we're not now omitting 0, then our base case changes to P of 1. And similarly, for each k in the natural numbers, now we will put in a plus there, and P of n is true for each natural number n, now becomes n plus. And actually, as you do the reading for 6.1, what you'll see is that you can make this change to the principle of mathematical induction so that you start, say, n equals to 4 or n equals to 5, and then what mathematical induction will say is that the statement is true for all n greater than or equal to the one that you started. And so this is a very versatile statement in that we can change the starting case. So with that, let's do our scratch work. And so we want to go ahead and do the inductive step. And so we're going to assume that if we have the sum from 1 to n of the first odd integers, The first odd integer being, of course, 1. So I'm going to write this as 2j minus 1. So now if I plug in j is equal to 1, I'm going to have over here that this will be 2 minus 1, which is 1. And then we're going to go ahead and say that this here is equal to n squared. And so this is a translation of this statement here. We're adding the first n odd integers, and we're saying that this is equal to n squared. So we're going to assume this. And what we want to show is if we go and add the first n plus 1 odd integers, that we get back n plus 1 quantity squared. So with that, let us now consider the sum from 1 to n plus 1. So now we're going to be adding the first n plus 1 odd integers. We're going to need more space, so I just brought it down. So if we evaluate this, we get back 2 n plus 1, we're plugging n plus 1 into the sum, minus 1, plus the sum from j is equal to 1, but now we're going only to n since we already evaluated at n plus 1, 2j plus 1. So now this becomes 2n plus 2 minus 1, so this is this part over here, and so that's just going to become 2n plus 1. And now, by assumption, this is equal to n squared, since this here is the sum of the first n odd integers, and so that's equal to n squared. But n squared plus 2n plus 1 is equal to n plus 1 quantity squared. And so now that shows the inductive step. Because now that's saying that the statement p of n plus 1 is true. So now we have our basis for our argument. So now let's actually formally prove this. So here's the proof. And when writing a proof by induction, and this is where my writing is going to differ from the book, and something that I highly encourage you to do, is to explicitly say what the statement that you're trying to prove is. So in other words, write down p of n. So let p of n be the statement where now we have the sum from j equals 1 through n of 2j minus 1 is equal to n squared. And so now we have our statement, and so we're going to prove this. So we proceed by induction on n. Now we're going to go ahead, do our base case. Our base case is going to be n equals to 1. For our base case, we have that the sum, and technically we don't have to go ahead and do this. I mean, I'm writing everything down, but we can just say 2j minus 1 or 2n minus 1. So this is equal to 1, which is the same as 1 squared, and so p of 1 is true. And so now we have established the base case. We have p of 1. Now suppose that p of n, or p of k, is true for some k. So now we're moving into the induction step. And if you compare my writing style with the book, you'll see that in the book, Belleman explicitly says base case, and then says p of 1 is true, and then says induction step, and then does the induction step afterwards. I'm writing it in this form as this is what is most common in other mathematical texts, and so that way you have two ways of seeing how a proof by induction can be written down. And so we're going to suppose that p of k is true for some k. So in other words, we're taking k to be arbitrary. And so this is where we're taking into account that for every positive integer k, we're assuming that p of k is true for some k. But that k is chosen arbitrarily. And so I'm just going to write over here n plus, positive integer. Now, this assumption, which is part of our inductive step, is what is commonly referred to as the induction hypothesis. Induction or inductive hypothesis, both are commonly used. So just writing that out. And so now we can go ahead by our hypothesis we attain, and now I'm going to copy what we just wrote down in our scratch work. So here is our what we did for our scratch work. The only difference is I switched the n's to k's, since everything is now in terms of k. And since now we have shown that this is equal to k plus 1 quantity squared, so we attain this, which shows that p of k plus 1 is true. Now, by the principle of mathematical induction, which I'm going to abbreviate as PMI, we conclude that p of k, p of n, is true for each positive integer n. And so we are done. We now have established this, because upon establishing this for every positive integer n, we get what we wanted to show. Since p of n, being true for every positive integer n, tells us that the sum of the first n odd integers is equal to n squared. And so we're done. And so in our next video, we're going to do another example where we utilize induction and then return back to the material from chapter 3.